Hey, so let's continue with mole concept. I'll try to explain the next topic. This is the second lecture of mole concept, and in the first lecture we had learned about the basics of mole, like just the basics of mole, like what is a mole, what is the number, and basic things that we learned was a definition of isotope, what a mole is, and and mass of one carbon 12 atom means 1/12 the mass of one carbon 12 atom, which is AMU. And we learned about mass number, and we learned about the relation between AMU and Avogadro's number, which is a mole. So further elaborating a bit on this number mole, earlier the definition was that this is the number of atoms in 12 grams of carbon 12 atom. That's where it was coming from. That was before the recent updates in the scientist community. So now the definition is just this, like this number is a mole. So anything having this number, anything like these many hydrogen atoms would be 1 mole of hydrogen atom, these many helium atoms would be 1 mole of helium atoms, like something like that, right? Okay, so now let's move on to learning how to calculate the number of moles. Right, so we are going to learn about how to calculate the number of moles. Calculation. Okay, so I bet you can do the you can derive the formulas like with your basic math skills. uh, let me explain. Right, let's just say that you have a dozen, right? As we took in the last video, the example we took in the last video, like a dozen has 12 of anything, right? A dozen has 12 of something. So now if I have 48 bananas, if me has 48 bananas, then I'm asking you, how many dozen bananas do I have? So what do you say? Obviously you'll say 4 dozen, right? But where did this 4 come from? You know what you did there? In your mind, you took the number of bananas I had and divided it with how big the unit is, like how many bananas are there in a dozen. So there are 12, so you get 4, right? So in the same way, think about it in the same way. If I have, let's just say an example, if I have 12.046 into 10 raised to 23 atoms, or right, atoms of hydrogen, and 1 mole of anything is 6.023 into 10 raised to 23, right? Then can you tell me how many moles of atom I have? Like how many moles of hydrogen do I have? Yeah, so what you simply do is you'll tell me easily, you'll be able to say that I have 2 moles. That implies moles of hydrogen, right? It's simple, right? I mean, what you just did there was dividing the number of particles, number of atoms in this case, but in general it would be number of particles, with number of particles in a mole, right? Which is Na, or Avogadro's number, which is 6.022 10 raised to 23. Okay, so this 6.023, somewhere it's 6.023 and somewhere it's 6.022. It doesn't really matter a lot, because usually if in an exam, if any competitive exam you're going to appear for, they'll give this value in the question that you needed. Like if they think that you need to use the number and use Avogadro's number, then they'll directly give you this value. so you don't have to worry about it. But in general, you can use it as 6.023 or 6.022. That's like, it doesn't really matter because it's just a fractions difference, right? Anyways, so 2 moles, so number of particles. So what you did here was divide this number with this number, right? Like you're dividing the number of, you see, you have to we have to fundamentally understand that what is going on here. So in that, like, instead of just directly remembering formula, we have to understand what's going on here. So I had these many atoms of hydrogen, and in a mole there are these many particles, so that implies that there are 2 moles of hydrogen, right? So what you did there was dividing the number of particles that we had, which was 12.046 into 10 raised to 23, with the number of particles in a mole, and that way you got the number of moles, right? Do you feel it? I think that was the best explanation that I could give. I hope you understood how this formula is coming. So this is the first formula, right? So this is the first formula. Okay, so this is the first formula. Yeah. Okay, from here let's derive one more formula. Okay, number of moles equal to, now you yourself will fill this. Okay, I mean, I won't even tell you directly, but you will, and then I'll explain it to you indirectly, and then you'll understand. Okay, now if the mass of, if I have, let's say 10 grams mass of hydrogen, like 10 grams of hydrogen, if I have 10 grams of hydrogen, and 10 grams is the mass of hydrogen that I have. Okay, and I'm asking you, how many moles of hydrogen do I have? What do you say? Like, what do you do here? What do you actually do here? What you're doing here is, it's very simple. You just have to understand what's going on here. You know the mass of 1 mole of hydrogen. If you know the mass of 1 mole of hydrogen equals, let's just say 1 gram, it is 1 gram actually. Okay, then how many moles of hydrogen do I have? It's simple, right? I mean, you got it, right? I think I was able to explain it. I don't know. Yeah. So 10 grams and 1 gram of hydrogen. Okay, so let me just explain it to you in another way, because I don't think you understood what I was trying to convey here, or maybe I was not able to convey what I wanted to convey to you guys. Okay, let me just try in another way. See, this is number of particles divided by Na, that you agree is number of moles. That we derived, that you agree, because I think I explained it well enough that you understood. Now, in this number of particles by Na, you multiply and divide mass of one particle. So this is mass of one particle. Okay, you multiplying and dividing it with mass of one particle. Think about it, because it shouldn't make a difference, right? Because you're multiplying and dividing by the same number, so that it will get cancelled and you'll get this initial equation back. So you're just multiplying and dividing it by mass of one particle. And what are you getting in the numerator? Think about it and say what you're going to get in the numerator. You're going to get the mass of particles that you have, right? Mass of particles divided by, what you're going to get is mass of 1 mole of that particle, right? And this mass, and okay, this is another definition, that mass of 1 mole of a particle or of actually of a particle is given by is named, is termed molar mass, right? Is termed molar mass. It's very simple, right? Molar mass, right? Mass of 1 mole of a particle is the molar mass of that substance. It's simple. Like, it's easy name, right? Mole mass, right? Molar mass. Okay, so this is a definition, good definition. You should remember this one. This is a good definition. Okay, so this is mass. So what is happening here? Molar mass, and molar mass is represented by m. Okay, m, capital M, capital M, capital M. So mass we have, or mass given in the question, they may give, like, I mean, that there are 10 grams of hydrogen, like right here there are 10 grams of hydrogen and mass of 1 mole of hydrogen. See, now you understand probably what I was trying to explain here, but then I thought that I didn't explain what molar mass is, and then so maybe the different approach was better. I think this was better. Yeah, so mass given in the question, or mass of the particles that you have divided by m, and that is another way to find number of moles. Oh, sorry. Yeah, so it's green. Important formula. Okay, important formula. It's pretty important formula. Okay, I hope you understood what I was trying to explain here. That number of particles by Na, you know already that how we got it equal to number of moles, and then we just multiply and divide with mass of one particle to get the mass of total mass of particles divided by the mass of 1 mole of that particle, and that mass of 1 mole of that particle is called molar mass, and it is like molar mass by mass given by molar mass. That is another formula for number of moles. So the first formula that we learned was number of moles equals number of particles by Na, which is Avogadro's number, and number of moles equals mass given by molar mass. Now there is another formula, third formula. Okay, I should just turn the page. Okay, so till now what are the formulas that we learned? We learned the formulas, sorry, I should just straighten it. Okay, so till now we learned the formulas: number of moles, number of moles equals number of particles divided by number of particles in a mole. It's better, that's a better way to say that, because every time you say that you're understanding what's going on. And it is also equal to mass of particles that we have, or mass given these particles, and divided by mass of 1 mole of the same particle, which is a molar mass, right? Okay, now another way of understanding, finding number of moles. So first off, let's start off by rewriting this formula: mass given by molar mass, right? Mass of 1 mole of that substance. Now you guys probably know that density equals mass by volume. So volume would be equal to mass by density. I think you agree. Now if we are going to divide the numerator and denominator with density, there shouldn't be any problem, right? Because we are multiplying with the same number, which is 1 by d, right? Just think about it, like m, which is mass given, times 1 by d divided by molar mass times 1 by d, right? So this is the same thing as saying that given mass divided by density and molar mass divided by density, which is equal to, we know from this formula that this is volume. So volume of gas divided by volume of 1 mole of gas. Now the part what I need to explain it to you is that this formula actually only is working for gases. but whereas these formulas are for like anything, so like mass of solid, liquid or gas or anything, and number of particles in solid, liquid, gas or anything, doesn't really matter. But this formula is only for gas, and that too at a very specific condition, at STP or NTP, which is standard temperature and pressure or normal temperature and pressure, right? So what does this mean, standard temperature and pressure and normal temperature and pressure? Meaning when the temperature is when the pressure is 1 bar and temperature is 0 degree Kelvin, 0 degree Celsius or 273.15 degree Kelvin. So this is the absolute temperature in Kelvin, means temperature in Kelvin is called absolute temperature. And at STP and NTP, if the gas is at STP and NTP, only then can we use this formula of number of moles of gas. Now I need to explain why, right? Why only this formula can only be applied for gases. Yeah, that's the sentence. Why this formula can only be applied for gases and not any other thing? That's because what I feel is that it's because we know that volume of 1 mole of any gas is the same, because there's this law. Let's see, okay, one more thing. At STP and NTP, these gases would be considered ideal gases, and this is only for ideal gases, okay? Like this formula, and it's for ideal gases at STP and NTP. These things will come later on, I'm sorry, but yeah, it will come later on. But ideal gases are essentially gases that are like ideal, gases that are ideal. There are a set of rules which makes it ideal, like the gas molecules are perfectly spherical. We will learn about this in the gaseous state chapter, I think. Don't worry about it, but just know that this formula can be used only for gases, ideal gases at STP or NTP. And I can explain a bit about it, like why this formula is only used for gases. But ideal gas topic will be like a long time in your syllabus, I think 3 or 4 chapters next. Okay, so I'll explain why this is only for gases. So the thing is that volume of 1 mole of any gas, 1 mole of any ideal gas, volume of 1 mole of any ideal gas is essentially 22.4 liters. Okay, so we already know this volume, but volume of any liquid or volume of any solid will differ, right? Volume of 1 mole of anything would differ, and that's why I think we use this formula only for gases and not for any other substances, because I think it becomes easier for us to work with this, right? Now another thing that I wanted to tell you was that according to a recent update, this 22.4 liter is like the molar volume, right? Molar volume of any gas at STP NTP. Actually, according to a recent update in the IUPAC, according to IUPAC recent update, which is like International Union for Pure and Applied Chemistry, I think. Yeah, so according to their update, this 22.4 like molar volume of any gas at STP and NTP is not 22.4, it's actually 22.7. But our like syllabus has not been updated yet, and that is why I think this is still taken to be 22.4 only, but it's actually supposed to be 22.7 and not 22.4. But in questions, in numericals, you should always use this to be 22.4 liter per mole, and per mole, but since mole is 1, we are only taking mole 1, we don't write mole. It's just 22.4 liter, right? Okay, so these are the major ways of finding the moles. Now one more thing that I wanted to say was that at STP and NTP. So what if the gas is not at STP and NTP? What if the ideal gas is not at STP and NTP and is at some other temperature, some other pressure, something else, right? So what do we use then? Actually, we are supposed to learn this topic a bit later in as I said, in gaseous state. But now because since we are learning about how to calculate moles, I think now we should learn about this too, which is the formula of PV equals nRT, right? PV equals nRT, which was derived by 4 experimental gas laws, meaning like 4 scientists did experiments and derived 4 gas laws based on those experiments, and this relation is called the ideal gas equation. Which is a very good equation. We will learn about it later on in gaseous state chapter, and we'll also learn about the experimental gas laws in that chapter. But for now, we just need to know that this is the ideal gas equation, and if the pressure and volume and temperature of the gas are different, right? If the pressure, volume, temperature or something is different, not STP and TP, then we can calculate this moles from this formula, PV by RT, right? PV by RT, we can calculate it by this formula. And here where I'll elaborate, P is pressure, T is absolute temperature, which is temperature in Kelvin, always remember. Which is temperature in Kelvin. Okay, so temperature in Kelvin, you I think easily understand how to change Kelvin to Celsius and Celsius to Kelvin. It's easy that 0 degrees Celsius is equal to 273. You can just take 273, it doesn't really matter. 0.15 is not usually taken Kelvin. So if you want any any value in Kelvin, so you just take Kelvin is equal to temperature in Kelvin, T in Kelvin is equal to T in Celsius plus 273. So temperature in Celsius plus 273 would give you temperature in Kelvin. This is how to find the absolute temperature, and absolute temperature, as I told you, is temperature in Kelvin. Okay, so P is pressure, T is absolute temperature, V is the volume, and R is actually the gas constant, right? It's R is a gas constant, which was, since I told you that these are experimental gas laws, so we could only find the proportionality, and hence there is a gas constant. This R is actually having many values. R is equal to 0.0821. The units were, always remember, writing units is very very important, because maybe sometimes you forget the formula itself, but if you remember the units, you can rederive the formula from it. Okay, so R is essentially this 0.0821. It's liter mole. Wait, let me check what the units were. Yeah, okay, so it is liter ATM per Kelvin mole, right? Liter ATM per Kelvin mole. It's very simple actually, but if you just take R equal to PV by NR, liter ATM, liter from volume, ATM from pressure, per Kelvin mole, right? So Kelvin is from temperature, and mole is from mole, right? This is simple. Okay, so this is the basic value, and there are many different values in different units, and this value can easily be written as 1 by 12, the same unit. 1 by 12, the same unit. So if you calculate 1 by 12, you approximately get this value itself. Okay, so if the gas is not at STP and NTP, then you can use this formula also, which is called the ideal gas equation. And if the gas is at STP and NTP, then number of moles we have already derived is volume of gas divided by, okay, so volume of gas in liter, let me remind you, volume of gas in liter, obviously, because if you're taking molar volume in liter, then volume of gas should also be in liters. Okay, so I hope you understood this lecture, what I taught, what I tried to explain in this lecture. I hope you guys understood. We have finished the basics of mole now. Yeah, we have finished the basics of mole, and in the next lecture we'll learn about average atomic mass, maybe even do a few questions. Okay, so that is it. Take care, okay? And always remember, like, the basic philosophy is, what I'm trying to do here is, I'm trying to teach every why that comes into my mind, right? Every time I think why, like, I encourage you guys to think too, right? Every time I say why is this, every time I say something like number of moles is volume of gas by 22.4, I encourage you to think why, right? I hope you understood why in this lecture. I hope you understood why of most things in this lecture. And I'm sorry if you couldn't if I couldn't explain the why of some things in this lecture, but I'm sure you will be able to understand them as we progress through the syllabus. So don't worry about it, but I hope I explained a lot of whys which weren't. Okay, take care guys.